I want to talk to you a little bit about graphing polar functions. Y'all have not had a lot of experience with this. And so I want to look at the graph of a couple of these and show you how to look at figuring out. Because what we're going to have to do, that you've seen in these last two sections, is we're going to have to be able to calculate the area of a region enclosed by a polar graph, or the area enclosed or between two polar graphs. And to do that, we're going to have to figure out what angles to integrate from. So we need to be able to tell when, for instance, what the angle is when this region begins to be formed. So I want to relate this to the unit circle, and I've left it blank because it's expected that you know the values that go on this unit circle, and this is going to help you visualize what's happening here. So if we're looking at the function r equals theta sine squared theta. Now, R1, if we're looking at values from theta is 0 to 2 pi, for instance, as long as theta is a positive value, this quantity is always going to be positive. So R is going to always be in the direction of theta. Remember, I told you, if we have pi over 2 as our angle, then pi over 2 is in this direction from the unit circle, from the center of the circle, from the origin, right? Pi over 2 is straight up on the positive y-axis. And so if we plugged in pi over 2 here, then theta would equal pi over 2, and sine squared theta would be the square root of 2, or sorry, 1. This would be pi over 2, and sine squared theta would be 1, and we square that, we get 1. So this value would be pi over 2. So the R, this point, when we plug in pi over 2 for theta, the angle is pi over 2, and the R, the distance, is pi over 2. So we would go pi over 2 units from the origin. And so that tells me that's where this point's formed. Now, when theta is 0, then theta is 0, sine is 0, so the value is 0. So the point 0, 0 is going to start there if we graph from 0 to pi over 2. And when we get to pi over 2, we're going to be here. And so then if we think, when is the next time on the circle as we roll around from 0 to pi over 2, when's the next time the sine's going to be 0? So if we look at that, and we are going around the circle, and at pi over 2, we know the point was here. We continue on around, and when we get to the angle pi, the sine is 0 again. So this graph from 0 to pi is going to be this part of the function. I want to show you that on a calculator. So here I've got the function graph, but I want to show you this. I'm going to go to Window, and I had graphed it from 0 to pi over 2. But this time I'm going to graph it from 0 to pi to show you that only forms this top part of the circle. And you'll see when you watch this graph, you'll see that it follows exactly this path. It starts at the origin, it comes around this way, and then it gets to here when theta is pi. So we want to tell it to graph, and you watch what happens on the graph and watch it form this part of the graph. And I need you to be able to visualize this even on a non-calculator part, because some of these questions will be on a non-calculator part. So we hit graph, it formed that part of the graph of this polar curve. So now let's think about what happens when we go past pi on the unit circle. Now the sine is negative down here, but since we're squaring the sine, the R is still going to be positive. So when we get to, say for instance, 7 pi over 6, that angle is about right here, and the sine is negative 1/2. So sine squared is going to be positive 1/4. When we square negative 1/2, we get 1/4. And so it's going to be 1/4 times 7 pi over 6. And so that's going to be in this direction, but however far 7 pi over 6 divided by 4 is, or 1/4 7 pi over 6. So now, once we get past pi, as we're going to rotate through our input angles, our graph is forming this part of the function. All right, so we're going to go over here to the calculator, and this time we're going to graph this, and we're going to set our window. We're going to set our theta minimum from pi and our theta maximum to 2 pi. And I want you to see that it forms this part of the region. So I'm going to hit enter and graph. And this is the part of the function that's covered. So you're going to have to, if I had asked you to find this shaded region, you would have to make an integral from 0 to pi in order to calculate the area of that region. If I ask you to find this shaded region, you'll need to integrate from pi, because that's when this region starts to be formed, until you get to 2 pi when it's closed. So how do we go about this? Whoops, let's say, get rid of that. Let's think about, as we integrate, or let's go ahead and do another form of graph, then we'll do the integrals on another video. Let's look at the graph of this function, 5 minus 5 sine pi. Now, you see the graph already, so I'm going to go ahead and change in the calculator. Change our y equals to 5 minus 5 sine pi, or sine theta, sorry. Now, the window, we saw that that's going to go down to -10, so I'm going to go ahead and change my y min to -10 so I can see that entire graph. I want to talk through this before I show you the graph, though. So let's talk about what happens with our angles. Again, we're going to look at the starting angles from 0 to 2 pi maybe. Now, we want to think through this because sometimes these graphs will go through a complete cycle in pi units, or pi over 2 units, or pi over 4 units. So we really need to think through these graphs. So first off, if we start at the angle 0, the sine is 0. So this part's going to be 0. So at theta equals 0, then the sine is going to be, or the r is going to be 5. So the angle is 0, and the sine is going to be 0. So it's going to be 5 minus 5 times 0. 5 is going to be the r value. So we're going to go over here and plot this point right here when the angle is 0. This is going to be that point. The r is 5 and the theta is 0. Now we think about when the next time the sine becomes 0, when the r value is going to become 0. Think about what's going to happen here. The sine is going to get larger. Sine is going to start getting larger. As we rotate from 0 to pi over 2, the sine is going to be getting larger, going from 0 to 1. As we do that, when the sine becomes 1, this becomes 5 minus 5 times 1, or 0. So once we get to pi over 2, where the sine is 1, the r value becomes 5 minus 5, or 0. So this part is formed from the r value 0, from the theta value 0 to pi over 2. Let's show you that on the graph. Let's change our theta min to 0 and our theta max to pi over 2. I'm going to hit graph, and you'll see this part of the curve form. That's what we were looking at here. It formed this part of the curve. Started at 5, went to here. So now what's going to happen when we go past pi over 2 and get to pi? First, when we get to pi, the sine is going to be 0 again. That's pretty interesting. So when we get to the sine to where pi is, the sine is going to be 0, which means this part of the curve is probably going to be formed next, because 5 minus 0 is going to be 5. So when we end up with the angle pi, we're going this direction, 5 units plotted here. So from 0, the theta is 0, here's pi over 2 when theta is pi over 2, here's when theta is pi. So if we go from 0 to pi when we build this graph, it'll see this top part of the curve. So let's go look at that on the calculator. Just so you can see it alongside. If I change my 0 to pi and hit graph, you'll see it form this part of the curve. I'm thinking through this because on a non-calculator part, this is what you're going to have to do. Now, you might already recognize what's going to happen as I go past pi. When I start into the third quadrant, r's, the sine is going to be negative. So this negative value for those angles is going to multiply times -5 to make this 5 plus something. And so the r values are going to be larger in the direction of the angle. And so that's why this curve is getting larger, farther away from the origin in this bottom half, because when the sine is negative, it's going to turn this quantity to positive and make it 5 plus some positive number. So if this looks like when we get to 3 pi over 2, the sine at 3 pi over 2 is -1. So if we do 5 minus 5 times -1, this is going to go together and make 5 plus 5, or 10. Now it's a graph where y is equal to -10, but remember, if the angle direction is 3 pi over 2 and the radius is 10, then we're 10 units in that direction, and that's why it's going to plot the point there. So then you can probably see from 3 pi over 2 to pi, or 2 pi, we're going to graph this part. So this function is going to be completed in 2 pi. Let's go ahead and do this. Window, change this to 3 pi over 2 now. So you can see it just graphs this part. So I'm going to change this to 3 times pi over 2. And it'll graph just that part. Looks like I need to make it a little bigger there. Let's make the window x min -7 and x max 7. And now if I go all the way to 2 pi, you'll see that it makes the complete graph. So I'm going to go theta min 0 to theta max 2 pi and hit graph. And you'll see the entire region. So that's a little bit about the way we graph polar curves. You need to calculate the values, get an idea where the important parts are, where the x-intercepts are, where the y-intercepts are, what's happening in the quadrant, so that you can figure out what angles we're going to have to integrate. Because if I wanted to get the area of this entire region enclosed by this graph, I'm going to have to integrate from 0 to pi over 2 to enclose the entire area. If I only wanted the top parts, I could integrate from 0 to pi. That would give me the area between the x-axis and on the top part here. Or I could go from 0 to pi over 2 and multiply the quantity by 2, because this graph is symmetric about the y-axis. If I only wanted the bottom parts, I would integrate from pi, where this part of the bottom part of the region started, until I got to 2 pi, because that's the part that forms that part of the region. So we'll work on that in another video. Right now, I just wanted you to see how we graph these polar curves.